My name's Harry Slatyer. I'm the lead quantum product engineer at Q-CTRL. In the last video, you saw a basic introduction to graphs. In this video, I'll show you how to perform computations using graphs. As before, you can visit our documentation website at docs.qcontrol.com to see several real-world examples where we use graphs to solve interesting quantum control problems. But for now, let's just go back to the basic notebook that we considered earlier. Recall that we have a simple single-qubit Hamiltonian, and we've defined a graph that represents a simulation of that system. In particular, we have a graph node that represents the time evolution operators of this system evaluated at a set of sample times. So let's actually calculate these. To perform any computation using the Q-CTRL Python package, you'll use functions in the qcontrol.functions namespace. When working with graphs, you have two options. If you're just looking to calculate the value in a graph, you can use the calculate graph function. On the other hand, if you're looking to do an optimization, you can define a graph that describes the objective function that you're looking to optimize and then pass that to the calculate optimization function. In this case, since we're just looking to do a simulation where we calculate the value of this time evolution operators object, we can use calculate graph. Calculate graph takes two inputs. The first is the graph object that, you may recall, just bundles together the different nodes in the graph. The second is a list of names of nodes that you want to output from the graph. So these are the nodes that will actually calculate in the cloud. In this case, all we need are the time evolution operators, which have the name operators. So once you've defined these inputs, you can call the function. You can easily extract the results as follows. Now you can see that operators is just a standard NumPy array, which you can manipulate using any of the NumPy techniques that you may be used to. We can also see that it's a three-dimensional array, where the outer dimension corresponds to the sample times that we requested. So as an example of what you can use with this, we could plot the evolution of the ground state population over time. So here you can see the evolution of the ground state population varying as a function of time. And this makes sense because you may recall that the control we defined was a linearly increasing Rabi rate. So that's why these oscillations increase in frequency over time. So to summarize, we've started with a simple single qubit Hamiltonian. We've defined a graph that represents a simulation of the system described by that Hamiltonian. We've used the calculate graph function in order to actually evaluate that graph. And remember, this computation happened on the cloud using high efficiency optimized hardware. And finally, we've extracted the results of the simulation and used them to plot the evolution of the ground state population over time. To see more examples of performing interesting computations using graphs, have a look at our user guides and application notes at the docs.qcontrol.com website. Thanks for listening.